Welcome to a special 15-year anniversary episode of Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office, or NNCO. Today, it's my pleasure to welcome Mark Reed, the Harold Hodgkinson Chair of Engineering and Applied Science at Yale University and founding director of the Yale Institute for Nanoscience and Quantum Engineering, a shared user facility for electron microscopy, scanning probe microscopy, and electron beam lithography. Prior to his appointment at Yale, he worked at Texas Instruments, where he demonstrated the first quantum dot device. Mark, thank you so much for taking the time to join us. To get us started, could you tell us a little bit about yourself and how you first got involved in nanotechnology?
Sure, I'd be glad to. It's a pleasure to talk to you today. So after I received my degree in physics, I was lucky enough to work at the Texas Instruments Research Labs in Dallas, Texas, and my charge was to explore the limits of electronics. This led to the exploration of a variety of quantum effect devices. At the time, nano was not the buzzword that it is today. In fact, we called the project ultra-small electronics. But what this did was really bring into focus what the possibility of nano was to be able to push the limits of electronics. So this was a fascinating time because we really lived through the origins of nanotechnology. In 1990, I moved to Yale and I continued my work in quantum effect devices and mesoscopic transport. And in this exploration branched out into a variety of various types of nanotechnologies related to electronics, including molecular electronics, and most recently, the intersection of electronics with biology. So I was lucky to be involved in the very start of the NNI. I was at some of the initial meetings that led to the formation of the NNI.
Since you were there since the beginning, you know that we're celebrating the 15-year anniversary. It's hard to imagine that it's been 15 years already. But from your perspective, can you share your thoughts on some of the key advances in nanotechnology that have been enabled by the NNI?
Well, it's hard to name just a few. It's been a wonderful 15 years. But I think the underlying major advance has been the transition from just the study of nanoscience to the engineering of nanotechnology. I think of the difference like this. Science studies what is. Engineering creates what never was. And so the advances I've seen over the last 15 years have been the real ability to engineer and manipulate things and create technologies on the very small scale. We have an unprecedented command of nanofabrication at the small length scales. Electronic devices now are on the order of a few nanometers in length, and that has allowed us to continue along the Moore's law to be able to create tremendously powerful systems that we have today. One of the things that really fuels innovations in both electronic and photonic technologies is the creation of new materials. And nanotech has really lent quite a bit of effort towards that and has created a whole range of possibilities in this area. And a lot of this would not be possible without the critical funding that NNI has produced for the national nanofabrication facilities around the country, that has taken the ability to do nanoscience and nanotechnology from individual people and individual research labs to a real vibrant network.
You've seen a lot of changes from your early days at Texas Instruments. Through your research, you mentioned Moore's law. Can you discuss the role that nanotechnology has played in these transformations?
Well, the people in the semiconductor industry, of which I was for quite a while, will tell you that they've been doing nanotech for 20 to 30 years by being able to scale devices down further. But the real challenges that people thought about when we first got into this was how to be able to make devices very small and how many more devices could you pack onto a chip. People for many years thought that was going to be the limitation. And it turned out that it wasn't. It was actually the amount of power that it needs to power the devices, and the worldwide nanotechnology is swinging their aim towards bringing all their tools to be able to attack that power. The challenge is still outstanding, but a lot of the enabling research is going on in people that are skilled in nanotechnology. But it isn't just computing technology. Some of the biggest impact of nanoscience is having impacts on things like energy. An example is the use of quantum dots, nanomaterials, to be able to make much more efficient light-emitting diodes. We've already seen record efficiencies produced by these, and those will continue and will have a tremendous impact both on energy usage and renewable energy.
That's a great example. I know that when we look at the research and development of quantum dots going back to the early 1980s and now really moving into mass market applications, as you mentioned, for lighting, but also for the flat panel displays, and it's been a really interesting transformation to both of those industries.
Many aspects of nanotechnology ranges from fabrication technologies and electronics, but some of its biggest impact that it's having is on various aspects of material science and applying that towards things like lighting, towards things like corrosion, towards things like water purification and green technologies.
I want to get your thoughts on quantum science. As founding director of the Institute for Nanoscience and Quantum Engineering, you know there's a lot of interest in quantum science and computing, and there's a new initiative that's moving forward. What is the role of nanotechnology in this area, both from the fundamental science perspective and with respect to the fabrication and characterization tools that you mentioned earlier?
Well, nanoscience is critical for all of these quantum engineering efforts, both from the fabrication and materials aspect, and the ability that we now have in nanotechnology to be able to precisely control structures and physical effects has really enabled the whole field of quantum information science and quantum engineering. There's wonderful science worldwide on quantum effect and atomic scale devices, down to the point of manipulating single atoms and single electrons and single spins. So the underlying physics and the underlying science of this is both beautiful and fascinating. Is this eventually going to be realized as a quantum computer? There's still tremendous challenges in being able to do that, and whether or not a quantum computer can be realized is still questionable. But that does not mean that the underlying science might not give rise to other ideas, both in information technology, security, and other areas. One must also think that during the time that one is trying to develop a quantum computing, what is regular technology going to do? And over the last few years, we've seen, while we've been working on quantum computers, over 100-fold increase in computer technology and conventional modes of computing, and that will continue forward.
You mentioned that what we consider more traditional computing has increased over 100-fold, but we're also seeing the need for different types of computing, edge computing, the distributed computing for distributed sensors and that type of things, the flexible tattoos, those types of technologies which may move away from the very centralized, like we saw with the march of Moore's Law and CMOS technologies improving. It may be fit for purpose looking at different types of computing moving forward, where quantum computing might not be appropriate for all applications. Is that your perspective?
Oh, absolutely. We've seen electronics morph into many different types of areas like you mentioned. And that kind of blending electronics with various types of applications and specific things like you mentioned, flexible electronics or portable devices, will continue on. I think one of the most interesting applications is the mix of electronics with biological systems to be able to meet everything from healthcare needs to eventual, say, human augmentation possibilities.
Well, I want to switch gears and go back to an earlier comment where you talked about the vibrant community of the NNI. Can you share some collaborations or other activities that have been made possible by this vibrant community, as you referred to it?
In the very early days of nanotechnology, you had to have your own facilities and tools to be able to do anything. And so the progress was relatively slow. But then one of the tremendous investments we made was in national facilities to make this technology available to everybody. But it wasn't just the availability of all these tools and the fabrication and the characterization. It was to bring everyone together. And the real advances were the people collaborating, talking to each other, doing similar fabrications, getting new ideas. So this entire infrastructure really evolved a collaborative spirit through nanoscience. Today, if you look at some of the teams of people doing various research projects, they're spread all over the country, and they've been brought together by these collaborative networks. An example of a project where some people at Yale were working with some people at Stanford and collaborating through the various NNI facilities to create the quietest laser that they just reported a few days ago. It's really enabled tremendously effective collaborative teams around the country.
So looking to the future, can you see challenges that currently face the country and the world where you feel that nanotechnology will play a role in solving?
Nano is going to have a tremendous impact on energy. One of the examples of quantum dots for more efficient LEDs. Various types of nanomaterials will impact many different areas that are related to energy, both from making more efficient water purification, which saves on energy, to be able to make more efficient and lighter materials. And a lot of that work has already started. I think one of the grand challenges will also be in environmental areas. Water purification, in fact, a project I'm also working on now, to be able to understand how one can make much more efficient separators, purifiers, using various types of nanomaterials and nanostructures, I think is one of the big challenges.
Mark, thank you so much for taking the time to talk with us today. Do you have any closing thoughts that you would like to share with our listeners?
I think NNI has been really pivotal in being able to bring together people for an ecosystem and common goals, to be able to define the directions that are most important for nanoscience, especially highlighting things like sustainability, energy, and water. And I think its signature initiatives are very important in being able to focus that work. The closing thought I'd like to give is the following. It's very difficult to predict things, especially in the future. If one would put yourself in 1950 and ask yourself what was 1980 going to look like, you'd probably come up with flying cars and nuclear-powered toasters. So be very careful of extrapolations. The types of things that we're looking for nanoscience to have an impact on, we can predict out a few years, and the initiatives that we've defined, I think, are obvious and very important. But the really important thing is look for the new opportunities. Look for the unexpected. In 1950, we never would have thought that we would have a phone that we carry around that has the computing power greater than the biggest computer that existed at the time. So I am very excited about what some of the new opportunities that nanoscience will enable.
Thank you for joining us today for this story from the NNI. If you would like to learn more about nanotechnology, please visit www.nano.gov or email us at info@nnco.nano.gov. And of course, check back here for more stories.